So let's try this example now. Solve the equation x minus 3 y prime plus 2y equals 0. Now, you definitely can use old techniques on this one, and that maybe is something good to do, but we're going to try to do it using series. Okay. Now, I don't have the solution ahead of time. This time I have to actually just come up with it. This should be fairly nice. Let's find out if it is. My generic power series is going to be an x to the n equals 0 to infinity. Then y prime is n equals 1 to infinity n x to the n. Okay, so the last one was really bad because of the actual series was bad. This isn't so bad. Now I have x minus 3 times y prime plus 2y. So what is that? X minus 3 times the sum n equals 1 to infinity n x to the n minus 1, minus 1 plus 2 times the original y n equals 0 to infinity of an x to the n. And this equals 0, of course, right? So we'll keep that in mind. And now we just kind of forge ahead here. So this is going to be x times the series. We're going to split this up with the x's and the not x's. N a sub n x to the n minus 1 minus 3 times that series. N equals 1 to infinity. N a n x to the n minus 1 plus 2 times n equals 0 to infinity of a sub n x to the n. Good. All right. Well, this first one, the x goes in. It's n equals 1 to infinity of n a sub n x to the n minus 3. Okay. Now, I'm going to want to put these three together. And so this one is already x to the n. This one is now x to the n. This one needs some fixing. So what we'll do is we will send this one up 1, right? So n minus 1 will become n. I'll have n plus 1, a sub n plus 1, x to the n. And that n starts at 0. Okay. So what do I have now? I have x to the n, x to the n, x to the n. That's great. I have 0, 0, ooh, bummer, 1. And check this out. This is one of those times, we'll make it 0. And why does that work? Well, that works because when n is 0, this is just 0 anyway. So I'm sort of adding a nothing term, and that's okay. And so I can just sort of combine all of these things together into a single series. N equals 0 to infinity of what? N a sub n minus 3n plus 1 plus a sub n plus 1 plus 2a sub n. And I think we can simplify that a little bit here. Can we? Well, let's see. I have n a sub n minus 3n a sub n plus 1 minus 3a sub n plus 1 plus 2a sub n. All right. We're going to use that thing from earlier, which is when you have a series that is equal to 0 for every x, then all of the coefficients are 0. And so what I can do here, did I give myself room? I did give myself room. What I can do here is I can actually just take all of this and set it equal to 0. So 0 equals n a sub n minus 3n a sub n plus 1 minus 3a sub n plus 1 plus 2a sub n. And I'm going to move some stuff around and try and solve for a sub n plus 1. All right, so let's combine some things. So I'm going to have negative 3n minus 3 times a sub n plus 1 plus n plus 2 times a sub n. Which means what? Well, let's move that over. I have that equals 0. So I have 3n plus 3 times a sub n plus 1 is equal to n plus 2 a sub n. And so a sub n plus 1 is equal to n plus 2 divided by 3n plus 3 a sub n. And so what this gives me is a recurrence relation between the terms. So if I know the first term, then I can find the second. And if I know the second, I can find the third. And if I know the third, I can find the fourth, and so on and so on. So what I'm going to do now is start plugging in the n's. So these start with n equals 0. Let's plug that in. So what happens when n equals 0? I have a sub 1 is equal to 2/3 a sub 0. Good. When n equals 1, I have a sub 2 is equal to 1 plus 2 is 3. This might be easier if I write it as 1/3 n plus 1 over n, 1 plus 2 over n plus 1. A sub n, that might be easier. So when n is 1, I get 3 over 2. So 1/3 times 3 over 2 a sub 1, which is 1/2, right? That's 1/2. And then what is a sub 1? Well, a sub 1 is 2/3 a sub 0. So that's 1/3 a sub 0. Okay. When n is equal to 2, I get a sub 3 is equal to, okay, 2 plus 2 is 4 over 3 a sub 2. And that is 4/9 times 1/3 a naught. So 4 over 3 cubed a sub naught. When n is equal to 3, I have a sub 4 is equal to 1/3 times 5/4 a sub 3, which is 5, 3 times 4, 4 times 3 to the 4th a naught. Those cancel and I get 5 over 3 to the 5th a naught. I think I might have tricked myself one here. I think this was supposed to be, maybe if I didn't cancel a 3 here, I think this is going to be better off to write 3 over 3 squared a naught. I think that's good. So 2, 3, 4, 5 over 3 squared, 3 cubed, 3 to the 5th. Let's do one more. N equals 4. I have a sub 5, 1/3, 6/5 times a to the 4th, which is 1/3, 6/5 times 5 over 3 to the 5th a naught, which is The 5's cancel, and I have 6. Okay, the pattern is now verified. 3 to the 6th a naught. So I think we can find the pattern now. This is going to be a sub n is equal to n plus 1 over 3 to the n plus 1 a naught. And so what we'll do is we'll take that thing and plug it back up into our original, which was there. And that gives me a series solution. So this means that y is equal to the sum n equals 0 to infinity of n plus 1 over 3 to the n plus 1 a naught x to the n. Now this a naught can just come out front. A naught n equals 0 to infinity of n plus 1 over 3 to the n plus 1 x to the n. And there is my power series solution. Now, this is a first order differential equation, so we expect it to have one parameter, which it does. And it would be some work to verify that this function is actually equal to the function that we would have gotten using the old techniques, and I will let you try that. We have one more series one more differential equation in this set of notes. Let's just power through it in this video rather than making its own. Okay, I'm sure that you are, half asleep by this point, and I get it. Why don't we solve one that we already know the answer to? Okay, so here you definitely can solve it just by looking at it using chapter 5 stuff. So let's go ahead and do it using series and see what happens. This should be, well, fun. It should be fun. Let's see if that happens. So here I get my y is my general power series, n equals 0 to infinity, a sub n x to the n. Y prime is going to be the sum n equals 1 to infinity, n a sub n x to the n minus 1. And y double prime is n equals 2 to infinity, n minus 1, a sub n x to the n minus 2. Okay. And easily enough, all I have to do is add those two together, so we're off to a good start. It is y double prime, n equals 2 to infinity, n minus 1, a sub n, x to the n minus 2 plus n equals 0 to infinity, a sub n, x to the n, right? And again, this equals 0. So I do have some bit of, well, let's find out what happens when I move the power. So that is n minus 2. To add them, I need them to both be n. So let's go ahead and do that. This needs to go up by 2. So it will be x to the n. That will be a sub n plus 2. And that'll be n plus 2, n plus 1, right? Send that up 2, send that up 2. Then this will go back down to 0. And that's good, because now those match, and so I don't have anything to worry about there. Okay, so we're good to go. They match. This is shaping up to be at least easy in that sense. I have n plus 2 times n plus 1, a sub n plus 2, plus a sub n. Okay? And so we will solve this one now. So 0 equals, so this, all those terms are 0, so I get n plus 2, n plus 1, a sub n plus 2, plus a n. And so then the thing to do here is, let's move that over, or maybe the easier way to do it is to think of that being moved over and then divide by this stuff. So that means that a sub n plus 2 is equal to negative a sub n over n plus 2, n plus 1. All right, here is my recurrence relation for the coefficients of this power series. I'm just going to assess how much space I have. Oh, I've got plenty. Okay, well, let's start. When n equals 0, what do I have? I have a2 is equal to minus a0 over 2 times 1. All right. When n equals 1, I have a sub 3 minus a sub 1. Okay, so n is 1, that's 3, that's 1. Divided by, it is, so just to note here, this number and this number match, if that makes this formula faster in your head. So 3 times 2, and then this one is one smaller than it. And that's all I can do with that one. Then when a is 2, I get a sub 4 equals minus a sub 2 over 4 times 3. Now I have some work to do here because I know a sub 2. That's going to be minus a sub 0 over, I have 4 times 3, and then this is now going to add a 2 times 1, 2 times 1. So that is a sub 0 over 4, 3, 2, 1. Okay. But n equals 3. A sub 5 is going to be minus a 3 over 5 times 4. Okay, minus a3. A3 is minus a1. 1. So we're looking back. We're going to put that into here. And so then I have 5, 4, and then the denominator will go down 3, 2. So I have a1 over 5, 4, 3, 2. I think we need to do a couple more. N equals 4, I have a6 minus a4, 6, 5. And then to that, I'm going to write minus, so what's a4? A4 is this thing, that thing will go there. A naught, 6, 5, 4, 3, 2, 1. I think we're starting to see the formula here. So a4 is going to be a naught over 4 factorial. This is a1 over 5 factorial. This is minus a naught over 6 factorial. This is minus a1 over 3 factorial, and that's minus a naught over 2 factorial. Let's do n is 5. I have a7 equals minus a5 over 7 times 6. a5 is here, so I have minus a1 over 7, 6, 5 factorial, and so that's minus a1 over 7 factorial. We are off to a pretty solid pattern here. Now what it looks like is happening is I'm having minus minus plus plus minus minus. So I'm going to have to think about how we fix that here on the next page. And it also looks like something is happening for the evens and the odds, okay? So what I want to do is I want to first pull out the evens here. So 2, 4, and 6, okay? So let's look at these. So when it's 2, it's minus. When it's 4, it's plus. When it's 6, it's minus. So what we're going to do is we're going to say, so for the even ones, what you're going to do is you're going to say if n is 2k, right? If n is 2k, then it's even, right? And so then a sub 2k is equal to a sub 0 over 2k factorial. Now, it alternates even and odd based on, it goes 2, 4. So 2 times 1, 2 times 2, 2 times 3. And so 2 times 1 is negative, 2 times 2 is positive, 2 times 3 is negative. And so when k is even, then it is positive. So it's just going to be negative 1 to the k, right? So when k is 1, it's negative. When k is 2, is positive, and so on and so on. Okay. Now, for the odds, I have two ways of doing this. I can do 2k minus 1 or 2k plus 1. And the way to go here is minus 1 because this is going to be k equals 1 and on. And k equals 1 and on here. If I do 2k plus 1, then I have to start at k equals 0. So it's kind of a good idea to start with the first k. All right? Oh, do I want to do that? No, I actually want to start at k equals 0. This one still works at k equals 0. That's okay. Because 0 factorial is 1. I just get a naught. That's good. I'm going to do 2k plus 1, so I'll start this one at 0 as well. Then a sub 2k plus 1 is going to be, these are all a1s, and they're all 2k plus 1 factorials. And then they are also going to go negative 1 to the k. All right? And that again starts at k equals 0 because when k equals 0, I have the first term, which is good. So a1 is just equal to a1, right? And that works. That's good. All right. So what have I done? Well, I have split up my series solution as y equals, okay, it's going to be k equals 0 to infinity of all this stuff. So it's these two things, negative 1 to the k, a0 over 2k factorial, plus negative 1 to the k, a1 over 2k plus 1 factorial. All of that. Oh, I have to put these with the x's, right? Move that over a little bit. These have x to the 2k's, and move that over. This has x to the 2k because these will be all of the even ones, and these will be all of the odd ones, 2k plus 1. So even and odd k's. Now what I'll do is I'll take this thing and pull that out, and I'll take this thing and pull it out and split this up into two different sums. So I have a naught times the sum k equals 0 to infinity, negative 1 to the k, 2k factorial x to the 2k, plus a1 sum k equals 0 to infinity, negative 1 to the k over 2k plus 1 factorial x to the 2k plus 1. And this is our series solution. However, these maybe look a little bit familiar to us, and I think we can go back and find them. So let's just remember this. Negative 1 to the k over 2k factorial times x to the 2k. Let's go back until we see a red box. There it is. Huh. That sure looks like negative 1 to the k, 2k factorial x to the 2k. That thing is cosine. And while we're at it, negative 1 to the k, 2k plus 1 factorial x to the 2k, that thing is sine. So what we really just did, as I go back to what I've got here, we just did sort of the hardest way possible of doing a naught cos x plus a1 sine x. And I think this is really interesting because the A naught and A1, like this solution is totally complete with the two parameters, right? If we went back and solved this using chapter 5 techniques, the characteristic equation has plus and minus I, and so the two solutions would be sine x and cos x. And so if we were to write the general solution down, it would look like A cos x plus B sine x, which is exactly what we got using series. And that is awesome. So that was, I think, a really fun exercise in showing how these series things do get along with our the things that we knew before. Okay. Now, as a fun fact here, our book has this, and I think it was really interesting. The sine and cosine functions are fully determined by the differential equation y prime plus y equals 0, of which they are the two naturally linearly independent solutions. Natural linearly independent solutions. So if you're looking for different ways to define sine and cosine, you can actually define sine and cosine like this as the solutions to this equation, and you can build backwards. So that is a really kind of a cool thing. And I think we're probably all asleep by now, but I hope that you kind of mustered up enough interest to make it through that, because I think that's a really cool thing to have happen. Okay. In the next one, we will move on to do recurrence relations for things that aren't so familiar. Okay. And I'll see you then.